This is question number 27 from June 2020 mathematical science paper. Let fx be e to the power ex e to the power minus x and gx is e to the power minus x squared. So we have to find which of the following statements are true. So we have this fx is e to the power minus x. Let us consider so gx is there, e to the power minus x squared. Okay. So let us consider two sequence. One sequence is xn, which we can write as log of n, and another sequence yn, which is minus log fn plus 1, and we have the sequence xn, mod of sequence xn minus mod of sequences yn is tends to 0 as n tends to infinity. Mod of f of xn minus mod of f of yn, within this mod it is equal to the e to the power log n minus e to the power log of n plus 1, right? So we can write it as n minus n plus 1 within mod, so it is equal to this 1, which is not tending to 0. So we can say that f is not uniformly continuous on R. So for our case the option 1 is wrong. So let's check with the option 2 then. If f of x is given e to the power minus of x, okay, and we know that e to the power x is a continuous function, right? So 1 by e to the power x or e to the power minus x, that is, and fx is a continuous function on R, right? It's continuous function on R, and f of x is also bounded, that is f prime x, so it is bounded on the semi-closed interval, that is a plus infinity, okay, where a is an element of the real space with mod of f prime x is less than equal to m, where m is greater than equal to 0. So we can say that f of x is uniformly continuous on the semi-closed interval, that is a plus infinity, right? So option 2 is correct. Now check with option 3. G is uniformly continuous on R. Now we have to find with the G. So here we know that G is given as g of x is nothing but e to the power minus x square, right? So if we put limit of x is tends to infinity gx and limit n x tends to infinity e to the power minus x square, so it will be come out as 0. Similarly, if we do for limit x tends to minus infinity g of x, so which will also come as 0, right? So both of them, this limit exist finitely, right? So we can say that G is continuous on R and endpoint limit exists finitely, right? It exists, both the endpoint limit exists finitely. So we can say that G is uniformly continuous. all over the space it is continuous, right? So option 3 is also correct. Okay, let us check with the option 4. So here we have been given this multiplication with fx gx. So it is e to the power minus x multiplied by e to the power minus x square, or we can write it as e to the power x multiplied by e to the power x square. Further simplifying it, we can find e to the power x square plus x. Okay. Now as limit x tends to minus infinity, so this f of x gx, it is 1 by infinity, it will be 0, and limit x tends to infinity, this f of x gx is also equal to 0. So we can say this is, it is continuous, f of x gx is continuous on R. This is right, the limit is continuous on R, so we can rightly say that fx gx is uniformly continuous on the real space R. So we can write this that uniformly continuous on. So option 4 is also correct. So we have the option 2, 3, 4. These 3 options are correct for the question number 67. So option 2, 3 and 4. Question 68 is define f of xy is x cubed by x square plus y square, where x and y is not equal to 0 and 0 for xy equal to 0. So which of the following statements are true? So we have the function f of xy is x cubed by x square plus y square, and it is 0. These two conditions are given, right? So for x and y not equal to 0 and it is equal to 0. So if we do put that y equal to mx, so f of x mx can be written as x cubed by x square plus mx whole square, which we simplify it as x by 1 plus m square, right? Now if we put the limit on both sides, that limit x comma y tends to 0, so this is f of x mx, so the limit will be xy tends to 0 comma 0 for x 1 by m square, it is nothing but 0. So we can say from here that f is continuous on, this f is continuous at, so f is continuous at 0 comma 0, right? So our option 1 is wrong, but option 2 is correct. Now we have to find the directional derivative. Okay. The directional derivative of f at 0 comma 0. Then we can write that limit h tends to 0, f of c plus hu minus f of c divided by h, which we can write it as limit h tends to 0 f of hu minus f of 0 divided by h. So which is that limit h tends to 0 f of hu1 and hu2 is two functions of h. So if we do this limit h tends to 0, so it is hu1 cube by h of hu1 square plus hu2 square. Simplifying it, we will get that limit h tends to 0. This is h cube u1 cube. This is also h cube u1 square plus u2 square, which is nothing but left with u1 cube by u1 square plus u2 square. So from here we can infer that all the directional derivative of f all directional derivative of f at 0 0 exist, right? So f is also differentiable. We can infer from here that f is also differentiable at 0 comma 0. So the option 4 is wrong for that, and option 3 is correct. So we have the option 2 and 3 for this question number 68. So f is continuous and at 0 comma 0, and all directional derivative of f at 0 comma 0 exist.